Hi all, we are continuing in chapter 8 now. So this next topic in chapter 8 is deducing valence electron configuration from trends in successive ionization energies. So to go through this topic, let's first define ionization energy. Ionization energy is the minimum energy, typically in kilojoules per mole, required to remove an electron from a gaseous atom in its ground state. So for something to be in its ground state, it's in its most stable state. It just means those electrons are not excited to higher energy levels. They're in their expected energy levels. So this is the amount of energy required to remove an electron from an atom. Because energy is required to pull the negatively charged electron away from the positively charged nucleus, so energy is needed to pull this electron away. So when that outer electron is released or pulled away or lost from an atom, that reaction leads to energy being absorbed. So energy is needed or energy is absorbed in order to remove an electron from an atom. So as we know, some atoms can lose 1 electron, 2 electron, even 3 electrons to form Fe3+, for example, that requires 3 electrons to be removed from the neutral atom of iron. So this correlates with ionization energy 1, 2, and 3. That would be, for example, just some generic element X. When we remove 1 electron, it becomes X+. That's the first ionization energy. Then X+, we can remove a second electron for this to become X2+. That is called our second ionization energy. Then X2+, if there's a third electron that can be easily removed, that's our third ionization energy. So I1, I2, and I3. The first electron, that's the easiest to remove. We need more and more energy as we try to remove more and more electrons. So first ionization energy is going to be the smallest, then the third ionization energy will be larger. We need more and more energy each time to remove an additional electron each time. And remember, energy needs to be inputted in order to remove that electron. It takes energy to remove a negatively charged electron that is pulled in or being attracted to the positively charged nucleus. So this is table 8.2 in your book. We have a value that mirrors the effective nuclear charge. Then we have each element, then the first, second, third, fourth, etc. ionization energies. You'll notice for hydrogen, there's only 1 electron, so we can only have a first ionization energy. There are not 2 electrons in order for there to be even a possible second ionization energy. Helium has 2 electrons, so this one could be removed. Then the second one is going to be larger. More energy is needed to remove that second electron compared to removing the first electron from helium. So depending on the element, it either takes some minimal amount of energy to remove an electron, or it'll get really large to remove a second. Sometimes it takes a lot of energy to even remove 1 electron. So for something like neon that already has a happy complete octet, it's not unexpected to see this number be really large because neon doesn't want any electrons removed. It's already in a happy complete octet. So this number is relatively large to even remove the first electron from neon. So here the second ionization energy is the energy required to remove a second electron from the gaseous ion. If 1 electron is already removed, then it's going to be in a -1 state. So the second ionization energy is the energy required to remove a second electron from an ion. The third ionization energy is the energy required to remove the third electron, and so on. So generally, ionization energies will increase as more electrons are removed. So the first ionization energy we expect to be the lowest, then the second ionization energy will increase for a given element. And when evaluating the ionization energies of a given element, the ionization energies corresponding to those valence electrons are much lower than those associated with core or inner shell electrons. In other words, it's easier to remove valence electrons, where valence electrons are those outer shell electrons with that highest value for N. It's much more difficult to remove inner shell electrons than valence shell electrons. So the ionization energies corresponding to valence electrons will be much lower than those of core or inner shell electrons. And so based on carbon's placement in the periodic table, we know carbon has 4 valence electrons and 6 total electrons. The first, second, third, and fourth ionization energies are lower compared to the 2 inner shell electrons, because these 4 valence electrons will be easier to remove, definitely compared to the 2 inner shell electrons. And so carbon with 6 electrons, we know that's 1s2, 2s2, so that's 4 electrons so far, then 2p2. So removing one of these electrons requires this much energy, the second electron, this much, a third, this much, a fourth, this much. Look at this difference here when we start to get into the inner shell electrons, or the 1s2 electrons. Those ionization energies to remove these electrons are really, really large. It takes a ton of energy to remove 2 electrons from this inner shell, or 1s2. These 2 are easier to remove than these 2, but these 2 inner shell electrons, where N is equal to 1, those are really, really difficult to remove, as we can see based on these very large ionization energies. So those 2 core electrons are really difficult to remove. But those valence electrons, they're easier to remove. Those electrons are in the outer shell. That's how we define valence electrons. And so just focusing on the first ionization energies for different elements, for hydrogen, that first ionization energy is a little bit lower than it is for helium. Helium has a filled N equal 1 shell, so 1s2 for helium. It's really difficult to remove 1 electron here compared to hydrogen that only has 1 electron to remove. Then for neon, that's also in a happy complete octet, just like helium is in a happy complete duet. Neon has a filled N equal 2 shell. So neon, we know, has 10 electrons. That's 1s2, 2s2, 2p6. With a filled N equal 2 shell, it's really difficult to remove any electrons from neon. It's already in a happy, satisfied, complete octet. When the shells are partially filled, it's easier to remove those electrons. Like we see for lithium, lithium only has 3 electrons, that's 1s2, 2s1. This electron here in a partially unfilled s subshell, 2s subshell to be specific, it doesn't take that much energy to pluck this 1 electron away. So that's why this has a much smaller first ionization energy compared to neon. Because it doesn't want any of these electrons removed, it takes a lot more energy to remove one of these electrons. So we see the same pattern here. When we have a filled outer shell, it's much more difficult to remove those electrons. These have a happy complete octet. They don't want any electrons removed, so we can see by their first ionization energies that are much larger. And so again, chapter 8 is focused on these trends. In the first part of chapter 8, we looked at the effective nuclear charge as well as atomic radii. Now here's this trend of the first ionization energy. The first ionization energy, or the energy required to remove one electron from the gaseous state of an atom, it increases going this direction, and it also increases going up a group. We talked about this one previously, where our noble gases will have a very large first ionization energy. They don't want any electrons removed. So it takes more and more energy as we move this direction to remove that first electron. Now going up a group, it increases going up a group. So less energy required to remove the first electron here compared to here. Why is that now? So this is n equal 1, n equal 2. The smaller the value for n, the closer those electrons are towards the nucleus. The closer these electrons are towards the nucleus for n equal 1, n equal 2, the harder it's going to be to remove an electron. So the closer an electron is to the nucleus, the harder it is to remove. It takes more and more energy as we get closer and closer to the nucleus, or as these n values decrease. And so electrons being removed in a higher value for n are easier to remove compared to lower values for n, where these electrons are closer to the nucleus. These electrons here are further from the nucleus. So higher values for n, further from the nucleus, a smaller ionization energy. Then smaller values for n, those electrons are closer to the nucleus. They're in shells that are closer to the nucleus. It's much harder to remove electrons that are so close to the nucleus. So these will all have larger ionization energies. So this trend here, we increase ionization energy from left to right. We increase the first ionization energy going up a group. So let's put this knowledge into a practice problem. We have the first 5 ionization energies here for a period 2 element. As a reminder on groups versus periods, this is period 1, this is period 2. So right now we're looking at these period 2 elements as possible answer choices. We need to look at this pattern of ionization energies where we see this huge jump after we've removed the first electron, the second electron, third electron, and fourth electron. So this follows a fairly predictable pattern of increasing ionization energy from the first, second, third, fourth electron. Then though, when we're trying to remove a fifth electron, we see a huge jump in ionization energy. So the first 4 electrons are fairly easy to remove. But the fifth electron here, this takes now a lot of energy to remove that fifth electron. So what this suggests is that atoms of this unknown element that we need to identify, they only have 4 valence electrons. Valence electrons are easier to remove. The ones that are easier to remove for this example are the first 4 electrons. That is hinting to us that this unknown element has 4 valence electrons. The fifth electron requires so much more energy that we're likely to think that that's a core electron or a non-valence electron. Non-valence electrons are a lot more difficult to remove. So in looking at period 2, which element has 4 valence electrons? Well, this has 1 valence electron, 2 valence electrons, 3 valence electrons, then 4 valence electrons. Carbon's electron configuration with 6 electrons in total, that's going to be 1s2, 2s2, that accounts for 4 electrons, then 2p2. So it matches up that these 4 electrons will be fairly easy to remove, but then we get to the lower value for n, or n equals 1, that next electron is going to be a lot more difficult to remove, leading to a much higher ionization energy. So here's this electron configuration for carbon. We know that helium really represents 1s2. So we can show carbon as 1s2, 2s2, 2p2, or just helium, 2s2, 2p2. These are the same thing. So it makes sense that the best guess we have is carbon because 4 valence electrons, fairly easy to remove. That 5th one, much more difficult to remove. Because we can narrow it down to the second period like we were told in the problem, it makes sense that we would guess that this unknown element is carbon. For a little more practice on ionization energies, let's look at 8.4 together. So in A, which atom should have a smaller first ionization energy, oxygen or sulfur? Then in B, which atom should have a higher second ionization energy, lithium or beryllium? To answer this, we should refresh ourselves on this trend. So increasing first ionization energy from left to right, increasing first ionization energy going up a group. So it increases left to right, the ionization energy, the first ionization energy, then it increases going up a group. So it increases left to right, increases going up a group. So for our strategy here, the first ionization energy decreases as we go down a group. So it increases going up a group, it decreases going down a group. This is because the outermost electron is further away from the nucleus and feels less attraction, so it takes less energy to remove. Then removal of the outermost electrons requires less energy if it's shielded by a filled inner shell of electrons. This just means that n equal 1 is more difficult to remove those electrons. When we go up an energy level to n equals 2, for example, these electrons will feel less of a pull because they're shielded or sort of blocked by these 2 electrons here. So the higher the value of the shell, the more electrons there are between the nucleus and these electrons here. The more electrons between the nucleus and these electrons, the easier it will be to remove those electrons. So electrons right next to the nucleus, more difficult to remove, than electrons further away are easier to remove. So let's think about problem A now, where we're looking at oxygen versus sulfur. For the first ionization energy, it's going to increase compared to sulfur, so oxygen will have a higher ionization energy than sulfur. Oxygen will have electrons in the 2p subshell, sulfur will have electrons in the 3p subshell. The smaller the value for n, the closer those electrons are to the nucleus, the more energy needed to remove an electron. N equal 3, the electron is further from the nucleus, the easier it's going to be to remove an electron. So oxygen will have a higher first ionization energy, sulfur will have a lower first ionization energy. They are both in group 6A, meaning they will both have 6 valence electrons. Oxygen has 8 total electrons, sulfur has 16 total electrons. Just looking at the outer shell for oxygen, this is going to fill 2s2, then 2p, 1, 2, 3, 4. Then sulfur here, just looking again at the outermost shell. When I say outermost shell, I mean the highest value for n. So n equal 2 here for oxygen. Sulfur, n is going to equal 3. So this fills the 3s2, then 3p, 1, 2, 3, 4. So they'll have similar outer shell electron configurations, 2s2, 2p4 for oxygen, 3s2, 3p4 for sulfur. So 2 and 2, 3 and 3, higher value for N, a smaller ionization energy. Those electrons are further from the nucleus. So lower ionization energy for a higher value for N. So here we predict that sulfur should have a smaller first ionization energy compared to oxygen. So next, let's think about B, so the second ionization energy, comparing lithium and beryllium. At least for the first ionization energy, beryllium will have a higher first ionization energy compared to lithium. Here we're asked about the second ionization energy though. For lithium and beryllium, lithium has 3 total electrons, so that's 1s2, 2s1. Beryllium, though, has 4 electrons, so that's 1s2, 2s2. For the first ionization energies, let's think about that. Based on the definition of ionization energy, it's removal of an electron from the gaseous state of an atom. So that's why we're noting it as lithium as a gas. The first one will be lithium plus an electron. For beryllium, that's going to be beryllium as a gas. That becomes Be plus an electron. This is technically still a gas, and this is technically also a gas. Based on the trend of just the first ionization energy, well, beryllium will have a higher first ionization energy compared to lithium. But again, we're not asked about the first, we're asked about the second. So this is technically higher than lithium, only looking at the first ionization energy so far. Because we're asked about the second ionization energy, we think about lithium plus losing even another electron, and beryllium plus losing yet another electron. So this becomes lithium 2 plus, this now becomes beryllium 2 plus. For lithium to lose its first electron, it loses it from this subshell, so 2s. For beryllium to lose 1 electron, it loses it also from 2s. For lithium's second ionization energy, it only has a 1s2 subshell that's filled. 1s2 to lose yet another electron is just 1s1. When beryllium lost its first electron here, it lost it from 2s2 to become 1s2, 2s1 for the first ionization energy. For the second ionization energy, it's going to lose yet another electron from 2s. So beryllium plus 1 is 1s1, 2s1. So for beryllium plus 1, that lost an electron from 2s2, leading to this being 1s2, 2s1. When this loses yet another electron, it has to be removed from the 2s subshell, leaving just 1s2 after beryllium has lost 2 electrons for its second ionization energy. So just focusing on the second ionization energies, lithium goes from 1s2 to 1s1. Beryllium goes from 1s2, 2s1 to just 1s2. Which transition will require more energy? Well, for beryllium, these 1s electrons are shielding this 2s electron. That means these 1s electrons are making it a little more easy for this electron to be removed from the 2s subshell. This means it's easier to remove this 2s1 electron from beryllium than it is to remove an electron from the 1s subshell for lithium. So this difference here will take more energy than this difference here. 1s2, 2s1 to just 1s2, this electron is fairly easily removed compared to another 1s electron like we see for lithium. So because 1s electrons shield those 2s electrons much more effectively than they shield each other, we predict that it should be easier to remove a 2s electron from beryllium than it is to remove another 1s electron from lithium. So this process should take less energy than this process. This 2s electron can be removed more easily than a 1s electron that has a filled subshell. And for this to be a filled subshell, it means this electron is in the same shell as its other electron. So 1s has 2 electrons here. These are in the same shell. There's not going to be any shielding. There's not going to be any electrons in between the nucleus and these 2 electrons, making the removal of one of these electrons really difficult. For beryllium, however, we're filling the 1s subshell, and in the 2s we have 1 electron. So these electrons here are in between the nucleus and this 1 electron, making this one easier to remove than one of these. So don't worry about this idea of metallic character here. We could check our work in looking at table 8.2. So in looking at table 8.2, the second ionization energy is beryllium, about 1,757. That is definitely much smaller than lithium's second ionization energy of over 7,000. So this second electron is easier to remove for beryllium than it is to remove a second electron for lithium. So our answers here do check out. So for A, sulfur should have a smaller first ionization energy compared to oxygen. And for B, beryllium will have a lower second ionization energy compared to lithium. Let's go into this topic now of understanding the definitions of ionization energy and electron affinity now. So for an atom to have electron affinity, it means it wants to pull those electrons in closer to its nucleus. It has affinity for electrons. So to define this, electron affinity is the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form a negatively charged anion. We can kind of think of this as the opposite of ionization energy, where we pluck away an electron. Here for electron affinity, we are adding an electron to an atom to create a negatively charged anion. So as we think of this somewhat in the opposite way of ionization energy was again removing an electron or removing a second electron or a third. This required an input of energy. Now for electron affinity, when an electron is accepted and that reaction then leads to energy being released. So ionization energy, remove an electron that requires energy, whereas electron affinity, we add an electron, energy is released. Energy is released because when we add an electron to a neutral atom, that electron is stabilized by the positively charged nucleus. So energy is released when that electron is added because the nucleus helps stabilize that negatively charged electron. So for instance, if we take neutral fluorine, we add an electron to become F-. The energy is a negative sign because energy is released. Oxygen as well, we add an electron to become O-, energy is released. A negative sign for enthalpy means that energy is released. Just like we saw for endothermic, exothermic reactions, energy is released. We see a negative sign. So although energy is released, we can still quantify the amount of electron affinity or attachment with a positive number. So we can ask how much energy was needed to add an electron. Well, this much energy was needed to add an electron. This much energy was needed, but when that electron was added to the nucleus, we release that amount of energy. So the delta H we see as a negative sign, but just quantifying the electron affinity on its own, we can say that as a positive number. How much energy is released? 328 kilojoules per mole of energy is released when we add an electron to fluorine. We'll look more at these signs here in just a bit. Again, the takeaways though, ionization energy, to remove an electron, energy is required. Electron affinity, where an electron is added, that means energy is released. So this is table 8.3, so on electron affinities in kilojoules per mole. So in general, electron affinity increases as we proceed across and up the periodic table. So electron affinity increases as we go from left to right and as we go up a group in the periodic table. But because noble gases have that happy complete duet for helium or octet for the other noble gases, they don't want to accept any additional electrons, so their electron affinity is actually less than 0. They don't want any additional electrons to be added to their nucleus, so it's essentially less than 0. So while energy is released when we add on that electron, we can still quantify an atom's electron affinity. What is fluorine's electron affinity? Well, it's this positive number. What happens when we add an electron to fluorine? Well, we do see that energy is released as we see this negative sign here. Let's look at electron affinities and the atomic numbers. We know the noble gases really don't want to accept an electron, so their electron affinity value is essentially 0 or even less than 0. They really don't want to take on another electron. The elements that do want to take on another electron, surprise, surprise, these are our halogens. The halogens have 7 valence electrons. They really want to add on another electron to reach a happy octet. The halogens have very large electron affinity values. Still though, when a halogen accepts an electron, there is a release of energy. Here though, we're just looking at how much they want to take on an electron. What is their electron affinity value? Well, very high for our halogens. So generally, our halogens have very high electron affinities. They really want to take on another electron. The noble gases have really low electron affinities. They don't want any more electrons. They already have that happy complete octet. And so for a happy complete octet, it means they want to fill their outer N or outer shell. And noble gases already have a full outer shell. They already have a full complete octet. That's where they don't want to take on any additional electrons, leading to very small electron affinity values for our noble gases. Let's try this practice problem. So we're considering this data for silicon. We have the atomic mass, electronegativity, electron affinity, ionization energy, and the heat of fusion. We've touched on this in thermo now. Atomic mass, we know we can look at the periodic table. We have not yet talked about electronegativity, but we have gone through now electron affinity and the ionization energy. We'll talk about electronegativity here in just a moment. We're going to answer all these questions. So one about the absorption or release of energy based on this taking on an electron. Then absorbing or releasing energy, when we see it takes on another electron, here it's Si2 plus versus Si plus. So in going through this practice problem, reactions 1 and 2 are variations on two standard types of atomic reactions in which outer electrons are added to or removed from an atom. In this reaction number 1, as an example, we are releasing an electron from the atom. In this second reaction, we are releasing another electron from this atom of sodium plus. Remember, if we are removing electrons, we're talking about the ionization energy. If we're talking about adding on electrons, that is talking about their electron affinity. So in these two reactions, we're definitely looking at their ionization energies because we're removing an electron and removing another electron. We can tell that because we see the electron on the product side of this reaction. So it starts out as sodium neutral, we lose an electron to form sodium plus, and we have a free electron now. This term ionization means that we're taking a neutral atom and it's losing or gaining some electrons to become either a cation or an anion. When a neutral atom undergoes ionization, it's becoming a cation or an anion by either losing electrons or gaining electrons. What do we know about ionization energy when we remove an electron? That we know requires an input of energy. We can tell that makes sense because these are positive signs for energy. This requires an input of energy to pluck away a negatively charged electron from a positively charged nucleus. It takes energy to do this. When ionization specifically refers to an atom losing outer electrons, we know we're talking about its ionization energy. So ionization, when we're losing electrons to become a cation, this requires an input of energy. This is what we've been talking about for the ionization energy. This is the first ionization energy because sodium is losing its first electron. For the second ionization energy, we expect that to be larger, which it is, because now it's losing a second electron. Now we talked about ionization energy as well as electron affinity. So a reaction in which a neutral atom gains an outer electron is called an electron attachment. When atoms gain electrons, this releases energy. And this makes sense based on these signs we see here. So negative signs for the energy because energy is released after that atom gains a negatively charged electron. So a free electron way out here is much less stable than an electron that comes closer to the nucleus. That's why we think of electron attachment as releasing energy. This electron is more stable the closer it gets to a positively charged nucleus. These opposite charges are stabilized, leading to a release of energy for electron attachment. The amount of energy that is released when electrons attach to a neutral atom is our electron affinity, or EA. This also means that for ionization energy, which requires energy, that's going to have the opposite sign as electron affinity or attachment, which we know releases energy. So the signs are very important to think about for electron attachment versus ionization energy. When we add on an electron for electron attachment, this releases energy. We'll see a negative sign. Whereas for ionization energy, this requires an input of energy. Negatively charged electrons don't want to be plucked away from a positively charged nucleus. That's why this requires an input of energy to remove that electron. An input of energy means we'll see a positive sign for energy. So rather than relying on a table, a periodic table, or table 8.2 or 8.3 in your book, it's better to think about the signs intuitively because then that will always make sense. This is as opposed to just trusting the sign of the ionization energy or the electron attachment that we see. So how do we reason through this again? Pulling an electron away from the attraction of a nucleus or ionization energy, this requires an input of energy. That negatively charged electron doesn't really want to be plucked away from that positively charged nucleus. Then alternatively, allowing an electron to respond to the attraction of a nucleus, the electron is stabilized by the positively charged nucleus. That will lead to a release of energy for electron attachment or electron affinity. So let's apply all this to our practice problem. I mentioned we would look at electronegativity. We'll actually look at that in chapter 9. So let's go through this practice problem. We just need the ideas of ionization energy and electron attachment here. So in reaction number 1, we have a silicon cation that is then losing an additional electron. So here a second electron is removed from the neutral atom of silicon. When we're talking about removing electrons, we're thinking about their ionization energy. So this reaction as listed shows the second ionization energy, Si plus losing an additional electron to become Si2 plus. Let's compare this one to the original reaction that was given in this table. This, as listed, is the reverse of the second ionization energy. Because we're taking Si2 plus, and now we're adding back an electron to become Si plus. So it's sort of the reverse of the second ionization energy, as well as electron attachment, but for the second electron. We're not seeing that though. We're taking Si2 plus, adding back an electron to have this still be Si plus. Do we have any information about the second electron attachment or the second ionization energy to give us what we need to know about this row? Well, all we have is the first electron affinity as well as the first ionization energy. So we don't have enough information to tell us about this first row. So we can't actually calculate this, but can we think about whether energy is being released or absorbed as the reaction is written? When we add an electron, will we expect energy to be released or absorbed? When we're adding back an electron, we expect energy to be released because that electron is stabilized by the positively charged nucleus. So that is all we can say for these first 3 rows. We're adding an electron, so energy is released, but we don't have any information about the reverse of the second ionization energy because all we're given here is the first electron affinity and the first ionization energy. Next, let's look at reaction 2. This reaction as written, this is not reaction 2, but this one as written shows the first ionization energy. We have the neutral atom, it loses the first electron is removed to form Si plus. As written in our practice problem, this is the reverse of the first ionization energy. This is also the same thing as an electron attachment. In just looking at this first one, when we attach an electron, is energy being released or absorbed? Well, we'll see the same thing as how we answered this one. We're adding on an electron. That electron is stabilized by the positively charged nucleus, leading to a release of energy. Now, how do we decide if we use this information or this information? An electron is being added, but it's also showing the reverse of the first ionization energy. Let's take a look back at our reactions that do describe electron affinity or attachment. We need to be really careful here because electron affinity is defined as the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. What do I mean by this? Well, this is neutral. Then we add on an electron to form an anion, or X minus. For silicon, for our practice problem, do we see a reaction that resembles this, where we have neutral silicon plus an electron forms the anion? Well, no, right? This is already a cation. We're adding an electron to form the neutral form of silicon. That means we don't really have something that describes this electron affinity. What reaction would describe this amount of energy? Well, that has to be neutral silicon. Then we add on one electron to then make this the anion form of silicon. This is the only way we could use this number for electron affinity. If we saw the neutral atom gain an electron to form the anion. As written here, this is showing Si plus an electron to form the neutral atom. That means this does not actually describe electron attachment in the sense for how it's truly defined. Yes, we're adding on an electron, but not to the neutral form of silicon. So instead of thinking this as electron affinity, it's really just the reverse of the first ionization energy. So which one of these numbers actually matches up with what we need? Well, it's the first ionization energy, but it's the reverse of this first ionization energy. So let's draw this out. This would be neutral silicon as a gas, then losing an electron to become Si plus. It's not written like this though, right? In our problem, we have Si plus, then gaining back an electron to form the neutral form of silicon. Again, we can't use the electron affinity number because we're not taking a neutral silicon, adding an electron to form Si minus. Instead, we're taking neutral silicon and seeing it separate into an electron and Si plus. This number describes neutral silicon losing an electron to form Si plus. In our problem, we see it written like this. So the energy associated with this second reaction is this amount of energy, so 786.5 kilojoules per mole. So as worded, we're just asked about the amount of energy being either absorbed or released. This means we don't need to show a sign. But if energy is being released, would this be a positive or negative sign? Energy being released means we'll see a negative sign. So technically, if we weren't asked about it being the absolute value, we would show that it would be negative. Here, though, we're just asked about the amount of energy being either absorbed or released. So either a negative sign or a positive sign, but we don't need to specify that because we're just asked about the amount and not the sign. Answering this tells us the sign, answering this tells us the sign. So be careful with problems like this and realize that the electron affinity is really only describing a neutral atom gaining an electron to become the anion form of that atom. Neither of these two reactions are showing that. This is Si2 plus gaining back an electron to become Si plus. This is Si plus gaining back an electron to become just neutral silicon. So here, release, no, because this was describing the reverse of the second ionization energy, and we weren't given any information about the second ionization energy of silicon. We could have looked it up in a table, but we're just looking at what was provided here in this practice problem in this table here. Then this one is a release of energy as well, because we're adding back an electron. And then we need to look at the first ionization energy. So this energy value describes the first ionization energy. Again, we're not looking at the electron affinity number because neither of these reactions are showing electron attachment or electron affinity. Let's do a little more practice on this together and go through example 8.5. So why are the electron affinities of the alkaline earth metals shown in table 8.3 either negative or small positive values? So a strategy for this, what are the electron configurations of our alkaline earth metals? Would the added electron to such an atom be held strongly by the nucleus? So electron affinity, we're thinking about adding on an electron, again, to the neutral form of the atom. Let's draw an example for beryllium. So for the electron attachment reaction, we're taking neutral beryllium, we're adding on an electron to then form the anion form of beryllium. To see if an electron will be stable when we add it to the neutral form of beryllium, let's look at the electron configurations. So n equal 1, 2, 3, 4, these are all in the S block. So beryllium then is going to have an outer shell of 2s2. Magnesium, 3s2, calcium, 4s2, and so on. I'm only writing out the 2s2, 3s2, and 4s2, but we know that other energy levels come before that. For example, for beryllium, what comes before the 2s2? Well, it fills 1s2, then it will fill the 2s2. If we're adding on another electron, where would that have to go? So 1s2, 2s2, next is 2p. We will enter a new subshell when we're forced to add on an electron to any of these alkaline earth metals. For magnesium, that's 3s2. So for any of these alkaline earth metals, they all end in 2s2, 3s2, 4s2, and so on. If we represent any of those alkaline earth metals as just capital M to represent a metal, adding on an electron will force that electron to go into the next subshell up. This additional electron would have to go into the 2p subshell, for example, if we're looking at beryllium. For that electron to be stabilized by the positively charged nucleus, well, it's not really going to be that stabilized because we have these other shells of electrons that are blocking its distance between the nucleus and this 2p subshell. So these lower levels of electrons, they're closer to the nucleus. That means that this electron has little tendency to be added to an atom like this. If it's added, it's still fairly farther away from the nucleus and it's blocked by these two layers. This is why these alkaline earth metals have very little tendency to actually pick up an extra electron. This one is filled and this one is filled. That extra electron would have to go up into the next subshell where it's really not that stabilized by the nucleus. So these were the main trends we went through in chapter 8, and then next time I talk to you will be for chapter 9. Again, if you have any questions at all about anything, definitely let me know. Hope you're all doing well, and I will talk to you soon.